And thanks to all of the organizers for organizing this webinar and for inviting me to giving me a chance to speak. So I'm going to talk today about some solution state NMR strategies for examining interactions between small molecules and nanoparticle surfaces. And our motivation for this is that the use of nanoparticles in our everyday life has been increasing. So from these nano bicycle chain loop to silver nanoparticles that are even used in baby products for their antibacterial properties, to even the problem of plastic nanoparticles. So this is a nice paper that came out a few years ago that showed that if you steep tea in a plastic tea bag, this actually releases billions of micro and nanoplastics into the tea that you drink. So this kind of shows a concern that with the increasing use of nanoparticles, they're going to find their way into the human body and into the environment. And one of these areas of concern in terms of nanoparticles is plastic nanoparticles. So we all know that plastic pollution is a large concern, and a lot of the plastic, whether we like it or not, ends up in world waterways. And over time, if a large plastic particle is in the ocean, for example, it's exposed to UV light, high salt concentrations, mechanical weathering, and all of these factors cause the plastic to break down into micro and eventually nanoscale plastic particles. And these nanoscale plastic particles are a good size to be mistaken for food by aquatic life. So the small fish will eat the plastic nanoparticles, the bigger fish will eat the small fish, we eventually eat the bigger fish. And so you might not think that humans ingesting plastic is a big deal, but another concern is that these plastic nanoparticles have a very large, very hydrophobic, very reactive surface area. So they also tend to absorb small molecules that may also be present in polluted waterways. So these could include pharmaceuticals, pesticides, carcinogens, all of these hydrophobic small molecules that we don't really want to be taken up by the nanoparticles and then potentially released into the body if they find their way into a hydrophobic environment. So it's important to have techniques whereby we can understand not only which small molecules bind to different nanoparticle surfaces, but also the mechanism for binding so that we can potentially design plastic that is going to not expose different reactive surfaces as it breaks down, or even regulatory policy. So if there's a particular molecule that's found in polluted water that tends to absorb to nanoscale plastic, maybe we want to screen for this in the fish that's intended for humans consumption. So to give you a little bit of introduction or a reminder about different relaxation times and related to correlation times of different molecules, a small molecule that's tumbling quickly in solution is going to have a long T2 relaxation time leading to narrow NMR lines. A large particle, such as a nanoparticle, on the other hand, is going to be moving slowly in solution, which leads to short T2 relaxation times and broad lines. And often, especially for the case of nanoparticles, this can lead to very severe broadening that is so severe that it's broadened into the baseline. So a lot of times we don't observe the NMR spectrum of nanoparticles in solution state NMR. And this leads to a few challenges if we want to observe something, whether it's a small molecule or a peptide or protein, absorbed onto the surface of a nanoparticle in solution state NMR. So a lot of studies have been done in solid state NMR, which is great. But a lot of times we do want to examine these interactions in solution because we're looking at things in aqueous pollution or in the environment, in a physiological environment in the body. So a lot of times we do want to study these interactions by solution state NMR. Well, one of the challenges is that when something binds to a nanoparticle surface, it is also going to be tumbling slowly at the same rate as the nanoparticle. So a lot of times we can't observe the bound species by solution state NMR because the broadening is too severe. Another challenge is that presumably only a small fraction of the ligand or a protein is going to be bound. So if we wanted to observe, let's say, this misfolded protein that's interacting with the nanoparticle surface, we're going to have to observe it in the presence of all of the bulk well-folded protein that also is going to be visible in our NMR spectrum. So for this reason, we need techniques that we can use to indirectly get information about the structure of something bound to a nanoparticle surface. And there are several solution state NMR techniques that have been used. So some of these are listed below. I'm going to talk about the first three today. So measuring signal intensity, relaxation time, and I'll focus on the STD NMR technique. If you would like to learn about DEST and/or relaxation dispersion NMR, I suggest this recent review article by the Venkatesh group. And Vincenzo has also done a Global NMR Discussion Group webinar that you can find on YouTube that I highly recommend. So I'm going to try to make my talk today orthogonal to his and try to talk about different techniques that he didn't talk about in his talk. If you're interested in learning about DOSI or transferred NOSI, this review by the Martins group is very nice. Another review by the Fitzke group that I also highly recommend came out recently as well. And I'm going to take a figure from this review to kind of explain the different regimes that we talk about in solution state NMR. So we often mention the slow, intermediate, or fast exchange regime. When we look at, let's say, a protein dimerizing, in the slow exchange regime, we're going to see a distinct peak for the free and bound protein. And the intensity is going to be related to the percent that is free or bound. In the intermediate exchange regime, we have line broadening. And then in the fast exchange regime, the line will sharpen up, and it will be at a chemical shift that is a weighted average of the chemical shift of the free and bound state. The difference when we're talking about binding to a nanoparticle, as opposed to just ligand protein dimerization or something like this, is that the nanoparticle has a much larger size and therefore a much slower rotational correlation time. And so the differences in T2 are going to be more drastic. The first thing that we see is that we don't generally see a peak for the bound ligand in the case of binding to a nanoparticle, because the broadening is so severe that it's just broadened into the baseline. The other difference is that in the fast exchange regime, it only takes a small amount of bound ligand to drastically perturb the spectrum that we see. So if we look at only 10% bound, we see that there's a very drastic change compared to 10% bound if we're just looking at protein dimerization. And even in the case of only 1% bound, we see still a drastic effect on the broadening of this peak in solution state NMR. So looking at the different regimes, if we are in the slow exchange regime or strong binding, we can examine the decrease in NMR signal intensity. So essentially the bound ligand in this case is going to be broadened into the baseline and it will disappear from our spectrum. So this system is a dye, and we're adding increasing amounts of polystyrene nanoparticles. In this case, we don't see an appreciable line broadening or changing chemical shift, but we do see a decrease in signal intensity as we increase the concentration of nanoparticles. If we have this case, we can model the decrease in signal intensity. So we can set up an equilibrium equation. The difference between looking at binding to a nanoparticle and as compared to, let's say, a protein ligand interaction is that for proteins, we typically have only one or maybe two or maybe a handful of binding sites per protein. In the case of nanoparticles, however, we may have a large number, maybe thousands of binding sites. So it might just be absorption or adsorption, non-specific interactions, but there is a potential that there may be many thousands of binding sites. So we're going to model this by letting P be the nanoparticle concentration, N be the number of binding sites on each nanoparticle, and then we have R to be the concentration of binding sites. So we can set up an ICE chart like we do in general chemistry and write the equation for KD, substituting in the equilibrium concentrations, and solve for X, which is the concentration of the bound complex. And knowing that the signal intensity in NMR that we observe is going to be proportional to the free ligand concentration, we can plug that in and we can plot the free ligand concentration as a function of nanoparticles added and pull out the number of binding sites and the KD. And often we can't determine these two values independently, but if we can get an educated guess at one, we can pull out the other. In the case of fast exchange, on the other hand, what we generally observe is a line broadening. We've looked at these three antibiotics as a model for small molecules that may be present in polluted waterways that might interact with nanoscale plastics. And we see that in the absence of nanoparticles, they all have very nice, sharp NMR lines. When we add polystyrene nanoparticles, though, we see, in this case, we see a signal intensity decrease as well as line broadening. And if you notice that for the levofloxacin, the signal intensity decrease is much more drastic than the other two antibiotics, and the line broadening as well. So if you notice, it takes a much lower concentration of nanoparticles to observe the same line broadening for levofloxacin as compared to the other two antibiotics. So this indicates that levofloxacin has many more binding sites on the nanoparticle surface than the other two antibiotics. We can quantify the line broadening by measuring the R2 relaxation. And if we measure the R2 relaxation rate as a function of added nanoparticle concentration, we can think of this as a relaxivity. And we can look at the slope of the line to determine which antibiotic is most perturbed by the presence of the nanoparticles. So looking at the slopes and looking at these different axes, we see that the levofloxacin has a much greater relaxivity, or the influence of the nanoparticles produces much greater relaxivity on the levofloxacin than the other two antibiotics. So this is in line with the signal intensity measurements indicating that levofloxacin has many more binding sites on the nanoparticle surface than the other two antibiotics. So next I'm going to talk about the STD NMR experiment. And the way that this works is if you have small molecules that are tumbling rapidly in solution, this will lead to narrow NMR lines. At the same time, if you have a large receptor in the same sample, it will have a broad NMR line. So you might see a broad hump, or it may be completely broadened into the baseline. The STD experiment consists of collecting two different spectra. The first is an off-resonance or reference spectrum. So in this spectrum, we're going to collect whether it's a 1D or a 2D NMR experiment. But before we do the experiment, we're going to saturate. And in the off-resonance spectrum, we're going to saturate at a frequency that is very far from where either the ligand or receptors resonate. So this really shouldn't perturb the system. It should just be our reference spectrum, and it should look identical to an unperturbed NMR spectrum. The second spectrum is an on-resonance spectrum. And in this spectrum, we're going to saturate for the same amount of time. But in this case, we want to saturate at a frequency where we hit the receptor, but where we don't disturb the ligand resonances. So this is often easy to do because the receptor has such a broad resonance. So a lot of times the frequency used is -1 ppm or 12 ppm. So this is in an area where you don't expect any ligand resonances, but even though you may not be able to see it, the receptor still has some, still resonates at that frequency. So you're able to hit the receptor and saturate the receptor protons by doing that saturation. So when you do this, if there are ligands that interact with the receptor surface during the saturation time, so in this case, the orange and the red ligands are interacting with the receptor surface, they will receive some of that saturation. And when they do, this leads to a decrease in signal intensity for those two ligands. On the other hand, ligands that don't interact with the receptor surface, so the green and the blue ligands in this case, have the same signal intensity in the on and off resonance spectrum. So we can then subtract the off resonance from the on resonance spectrum. And this immediately shows us a spectrum containing only signals from those molecules that interact with the receptor surface. So we see that the green and blue are canceled out, whereas the red and orange have some positive signal intensity here. So this STD experiment has been widely used in the drug discovery field, where the receptor is typically our target protein, and the ligands could be potential drug candidates, potential binding molecules. So you could kind of throw in a soup of potential small molecules that might interact with your receptor and easily pull out the spectrum of those molecules that bind. Another nice thing about this experiment is that it doesn't require that the receptor be able to be observed in solution state NMR. So there's no upper limit to the size of the receptor that could be studied using this technique. So we thought, let's try to use this technique to study small molecules interacting with the surface of nanoparticles. And so for this, we used what we call nano beads. So these are polystyrene beads or nanoparticles that we can purchase commercially, different sizes and with different functional groups on the surface that allow them to remain dispersed in solution. And for our first experiment, we looked at a mixture of glucose and ethanol with 20 nanometer polystyrene beads. And you can see in the STD difference experiment, you can clearly see the signals for the ethanol, meaning that the ethanol is interacting with the surface of the beads. And the signals that we see in the reference experiment, but not in the difference experiment, are due to the glucose. So in this case, it doesn't appear that the glucose is interacting with the surface of these polystyrene nanoparticles. One thing that you should always be careful about when you're doing these experiments is you want to make sure that you're not accidentally saturating the ligand resonances. So we always like to do a control experiment. So in this case, this is isopropanol interacting with 20 nanometer polystyrene beads. We see some STD effects for the isopropanol. Our control experiment is done for the same concentration of isopropanol, same saturation frequency, same saturation time, but without the nanoparticles or without the receptor. And in this case, we don't see any STD effect. So this gives us confidence that we're actually seeing polarization transfer from saturating the receptor and the saturation being transferred to the isopropanol instead of just accidentally saturating our ligand resonances or perturbing the ligand resonances directly during the saturation. One of the great things about the STD experiment is that it can be used for epitope mapping. So we all know that the real strength of NMR is in structure determination. And because the saturation transfer relies on intermolecular NOEs, it's expected there should be a 1/r⁶ distance dependence. So in other words, protons that are closer to the receptor surface in the bound state should be expected to have greater saturation transfer. And those that are farther from the receptor surface should have a less extent of saturation being transferred. So the STD effect, which we define as the difference intensity divided by the reference intensity, should decrease as a function of distance from the receptor surface. And this is actually a really great way to get information about structure indirectly. So by looking at the different STD effects on the different protons, we can tell which protons are located closer to the receptor surface and which are farther from the receptor surface in the bound configuration. So these are the seminal papers suggesting using STD NMR for epitope mapping, Mayer and Meyer. And we can see that they indeed are suggesting that when the proton that is closest to the receptor in the bound state is going to receive the highest saturation transfer, and those that are farther from the receptor in the bound state have a lower STD effect. So STD effect, however, depends on many different factors. Obviously, it depends on the distance between the receptor and the ligand proton. So this is what allows it to be used for epitope mapping. But it also depends on the saturation time. So as you increase the saturation time, the STD effect is going to increase until it reaches a plateau. So once all of the free ligand has been saturated and no more increasing the saturation time does not result in additional saturation, that effect will level off. So obviously the time that you saturate will influence the STD effect. The STD effect also depends on exchange lifetime, so the K on and K off rate, the KD, as well as the ligand receptor ratio. So all of these different effects influence the fraction of the free ligand that has been saturated. So obviously all of these will come into play in determining the STD effect. So we'll talk about how those relate in a few slides. It depends on the rotational correlation time of the complex. So this determines how easily the entire receptor can become saturated. And it depends on the ligand proton T1. So in fact, all of these effects come into play, and they're all sort of contained in this Corsima theory from Ramakrishna's lab in Alabama. So if you want to do a quantitative analysis of STD data, you can use this Corsima analysis to take into account all of these different effects and really get a very reliable distance between the ligand, proton, and receptor. So looking at all of these different influences, the first is the saturation time. So if we create an STD buildup curve, so if we measure the STD effect as a function of saturation time, it will eventually reach a maximum, which we'll call the maximum STD effect. And there's also an initial slope of this STD buildup curve. So we'll see why this is important in a minute. But we can model this exponential buildup as the STD effect being equal to the maximum STD effect times 1 minus e to the negative kt. We can then take the derivative and see that the initial slope, so the derivative ds dt at time t equals 0, is equal to S max times k. So obviously, if you increase the maximum STD effect, this initial slope will increase. Also, if you increase k, that means that the buildup time will be faster, so it will reach the maximum sooner, faster. That will also increase the initial slope. So either an increase in S max or k leads to an increase in the initial slope. The ligand receptor ratio also influences the STD effect. So if you, let's say you have this situation, this ligand receptor ratio, and you get this STD effect, if you increase the ligand receptor ratio by adding more ligands, this will drive the equilibrium towards the balanced state. However, you only have a certain number of free ligands that are able to be saturated and then dissociate from the receptor at a given time. And because the STD effect is the difference intensity divided by the reference intensity, this STD effect will be smaller as you have more bulk ligands that have not been saturated. So if you increase ligand receptor ratio, this will decrease the STD effect. The other way to think about it is you can decrease the ligand receptor ratio by adding more receptors. And this will allow more possibility for more ligands to bind. And this will obviously increase the STD effect. So the STD effect is inversely proportional to the ligand receptor ratio. And because of this, we can calculate an STD amplification factor, which is the STD effect that has been multiplied by the ligand receptor ratio. So this allows us to kind of compare STD effects that have been measured at different ligand receptor ratios. We can also, by measuring or calculating an STD buildup curve as a function of ligand receptor ratio, we can determine a KD. So if we look at the STD buildup curve, if we keep the receptor concentration the same, as we increase the ligand concentration, the STD effect is expected to decrease. We can then plot the initial slope of the buildup of the STD amplification factor as a function of ligand concentration and fit it to a Langmuir equation to pull out the KD. So looking at this, we'll look at this in a little bit more detail. If we plot this equation, there will be a position at which this value levels off. So this is the maximum STD amplification factor. If we look at half of that maximum and extrapolate down, this is the value of our KD. So in order to observe or in order to do this procedure, you need to be able to make measurements in the range of the KD. So if your KD is 2 millimolar, you need to be able to make these measurements in a range of millimolar. If it's micromolar, you need to be able to make these measurements in the range of micromolar. Because if you are in this region, let's say, it's just going to look linear. So you're not going to get that curve and be able to calculate a KD. And if you're way out here, it's just going to look flat. So a lot of times in NMR, we are limited in the different ligand concentrations that we're able to measure. On the low end, we know that we're all limited by the low sensitivity of NMR. And remember that even if you may be able to observe your ligand at the concentration that you like, the STD effect is a fraction of that signal intensity. So even if you have sufficient signal to noise at, let's say, 1 micromolar ligand, you need to also have sufficient signal to noise to be able to measure the STD effect. So on the low end, we're also often limited by the signal to noise of NMR, the sensitivity of NMR. And at the higher end, we could be limited by ligand solubility. So this method, again, only works if you're able to make these measurements at ligand concentrations that are relevant in the range of your KD for that particular system. The exchange rates K on and K off also influence the STD effect. Obviously, they're also related to KD. So if we have an equilibrium, K on and K off, and we have a STD effect, if the K on is too high, or if the K off is too small, the binding is too strong, in other words, you will have ligands associating with the receptor and becoming saturated. But if the K off is not fast enough, none of these ligands will dissociate into the free state where they are observed. So what we're observing in the STD effect is free ligands that have dissociated from the receptor surface and retain that saturation. So if the binding is too strong, we don't observe any STD effect. On the other hand, if the binding is too weak, then not enough ligands will bind to the receptor and be able to receive that saturation. So as a rule of thumb, the STD effect can be used for KDs between about 1 nanomolar and about 10 millimolar. So again, it's not good for every system, but when it is, the STD effect can really give us a lot of information. The last is the effect of the proton T1. So as the proton T1 decreases, the saturation of these free ligands will be driven back towards thermal equilibrium. So the magnetization will be driven back to thermal equilibrium by the T1. So if we add copper EDTA, something that's going to decrease the T1, we see that what happens is the STD effect reaches a lower maximum STD, but it reaches it faster. So if we look at, let's say, these different samples at a particular saturation time, like 1 second, and we compare, we see that there's a drastic difference between the samples with different T1s. However, if we look at the initial slope, because we're leading to a lower STD effect, but we're reaching it faster, there's less of an influence on the initial slope as compared to saturation at longer saturation times. And this is to be expected because if we extrapolate to T equals 0, relaxation hasn't had a chance to drive the magnetization back towards thermal equilibrium. So the moral of this story is you want to use the initial slope of the STD buildup curve rather than an STD effect at one particular saturation time when you're calculating KDs. So this has been shown very nicely in this paper by Jesus Angelo. They looked at measuring or calculating an STD or calculating KD from STD amplification factors at various different saturation times. And they saw that when you increase the saturation time that you use, the KD is overestimated. So this is due to relaxation and also due to ligand rebinding. So if you have a situation where a large percentage of your ligand is expected to be bound, there's a possibility that a ligand might bind, dissociate from the surface, from the receptor surface, and then during the saturation time, rebind. So that same ligand, rather than a fresh ligand, the same ligand comes in and rebinds, and this leads to a decrease in the STD effect because it's the same ligand again getting saturated. And that decrease in the STD effect leads to an overestimation of the KD. So in other words, if you want to obtain the KD that is closest to the true KD, it's best to map out the entire STD buildup curve and extrapolate to time t equals 0 or calculate the initial slope and compare initial slopes at various ligand concentrations to determine your KD. So with all of that, I'll give a few examples of things that we have done in our lab. So looking at the initial slope of the STD effect for this large floppy dye molecule, this was compared to binding to nanoparticles with a negative charge on the surface. So as expected, near the positive charge nitrogen of this molecule, we have the highest STD initial slopes. So in this case, I've set the highest slope to 100%, and then these are percentages of the highest initial slope. So near the positively charged nitrogen, we see the greatest initial slopes, and near the negatively charged sulfate group, we see the lowest initial slopes. So as expected, the positive side of the molecule, ligand wants to be closest to the negatively charged surface of the nanoparticle, and the negative side of the molecule wants to be farthest from the negatively charged nanoparticle in the balanced state. We looked at different amino acids as a model for molecules with different functional groups, again, binding to polystyrene nanoparticles with a negative charge. So we saw that positively charged amino acids like lysine had an observable STD effect. And what was kind of interesting was that the aromatic amino acids showed a very appreciable STD effect. So this tells us about our nanoparticle surfaces, in fact. So the fact that the aromatic amino acids are able to have these strong interactions indicates that there's maybe some porosity or something that's allowing the aromatic groups in the ligands to interact with the styrene, the aromatic styrene in the polystyrene nanoparticles. So by looking at this, we're actually able to get information about our nanoparticles and the surface and the porosity of these nanoparticles. And indeed, looking at the other aromatic amino acids, we saw that the highest initial slope of the STD buildup curve was always in the aromatic group. And in general, the aromatic protons had a higher initial slope of the STD buildup curve than the alpha and beta protons. Aside from aromatic interactions, we also saw that electrostatic effects were important in this binding. So to explore this in more detail, we looked at zwitterionic polystyrene beads that, again, we could purchase commercially. These have a mixture of carboxylate and amine groups on the surface, so that at low pH, they're positively charged, and at neutral and high pH, they are negatively charged. Again, looking at the different amino acids and looking at the highest initial slope of the buildup curve for each amino acid, we saw that the aromatic amino acids had the strongest interaction with these polystyrene nanoparticles. And the next highest interaction was among the positively charged amino acids. But importantly, these positively charged amino acids do not show any STD effect at pH 2, where the polystyrene nanoparticles are also expected to be positively charged. So this is showing again that electrostatic effects are important as well in driving the binding or the interaction between small molecules and polystyrene nanoparticle surfaces. In order to explore the electrostatic effects in more detail, we looked at the effect of salt concentration. So for the sample of arginine at pH 6, we saw that this was primarily driven by electrostatic effects. When we added a buffer, so we're going to increase the salt concentration by using a buffer rather than just simply adjusting the pH. We increase the salt concentration, and we see that the initial slope of the STD effect does decrease. So the salt is presumably shielding the positive and negative influences from each other and leading to a decrease in interaction. The last factor that we saw that was important in influencing interactions between these small molecules and the nanoparticles was London dispersion interactions in amino acids with long aliphatic side chains. So in order to explore this, we used a series of natural and unnatural amino acids with increasing side chain length. And it wasn't until the longest chain with 6 carbons that we saw an observable STD effect. So these others are just sort of cancellation. If you integrate these, they integrate to 0. So this shows that this dispersion interaction is also important in binding or interacting between the nanoparticles and small organic molecules. Lastly, I wanted to see how these different NMR techniques compared to other techniques such as optical spectroscopy. So for this, we used rhodamine B, which is a fluorescent dye. So we could also look at fluorescence. We looked at the rhodamine B interacting with different nanoparticles. So this set of nanoparticles has amidine groups on the surface, and this set has carboxylate groups on the surface. We saw that the spectrum of rhodamine is not significantly perturbed in the presence of the amidine nanoparticles, indicating that this molecule doesn't interact significantly with these nanoparticles with the amidine surface groups. Whereas when we added the carboxylate nanoparticles, we saw a significant line broadening, indicating that the rhodamine does interact with carboxylate modified nanoparticles. The STD experiments indicate the same results. So in the case of the rhodamine B interacting with amidine modified nanoparticles, we see only a very slight STD effect, so very small. Whereas when we use the carboxylate modified nanoparticles, the rhodamine B shows a significant STD effect up to 0.4. We can actually observe here. So the STD is also indicating that the rhodamine is interacting much more strongly with the carboxylate modified nanoparticles than with the amidine nanoparticles. We compared this to UV vis and fluorescence spectroscopy. These also give us the same answers. So in the case of the rhodamine, we don't see any shift in either the UV vis or fluorescence spectrum when we add the amidine nanoparticles. But in the case of carboxylate modified nanoparticles, we see a shift of a few wave numbers in both the UV vis and the fluorescence spectrum. Another fun thing that we can do with STD NMR is competition STD NMR. So if you remember these antibiotics that we were talking about at the beginning of the talk, where we've seen that levofloxacin binds more strongly than the other two antibiotics. So looking at amoxicillin and metronidazole, we have the STD buildup curve for each of these interacting with polystyrene nanoparticles. When we put the amoxicillin and metronidazole together in the same sample, again with the nanoparticles, we see that their STD buildup curves are not significantly changed, meaning that the amoxicillin and metronidazole don't influence the binding of each other to these polystyrene nanoparticles. On the other hand, when we added levofloxacin to a sample of either amoxicillin or metronidazole with the polystyrene beads, we saw a decrease in the STD buildup curve of both of these antibiotics. So this indicates that the levofloxacin is outcompeting the amoxicillin or the metronidazole for binding sites to these polystyrene nanoparticles. We can also use STD NMR to observe the influence of other molecules. So in the case of polluted waterways, dissolved organic matter might be a concern. So we've used tannic acid as a model for dissolved organic matter in polluted water. If we look at metronidazole in the presence of polystyrene nanoparticles, and then add tannic acid to that sample, we see a slight decrease in STD effect for peak 3, but the initial slope of the buildup curve is not significantly changed. And if we do our control sample, looking at metronidazole and tannic acid in the absence of nanoparticles, we don't see any STD effect as we expect. On the other hand, if we add tannic acid to a sample of levofloxacin and polystyrene nanoparticles, we see a decrease in the STD effect and also a decrease in the initial slope of the STD buildup curve. However, when we look at levofloxacin and tannic acid in the absence of polystyrene nanoparticles, we still see an STD effect for the levofloxacin. And this indicates that the tannic acid is perhaps forming aggregates, and the levofloxacin is interacting with these tannic acid aggregates, and this is the saturation transfer that we are seeing. So then in this case, we have levofloxacin binding to both tannic acid as well as polystyrene nanoparticles. So the STD buildup curve looks intermediate between the two. So we can use STD experiments to gain information about competition, as well as the influence of other interfering molecules on this binding. So to summarize, in the case of strong interactions or slow exchange, we can look at a decrease in NMR signal intensity to examine small molecules interacting with something large that's tumbling slowly in solutions such as nanoparticles. In the case of fast exchange, we can observe line broadening or increase in relaxation rate. And the STD NMR experiment is a very simple experiment to set up. It's very elegant. It can be used for epitope mapping, so we can gain structural information in an indirect manner. And also in favorable cases, we can use it to determine binding constants. Some disadvantages of the STD NMR technique are that it can only be used for a specific range of binding constants. So if the binding is too strong, you don't get any ligand dissociation from the receptor, and you don't see an STD effect. If the binding is too weak, you also don't see an STD effect. Another disadvantage is that we've used organic nanoparticles. So we've used polystyrene nanoparticles with a dipolar coupled network of protons in order to be able to completely saturate the receptor. So the STD experiment can't be used for organic nanoparticles, let's say, for example, for inorganic nanoparticles that don't have that dipolar coupled network of protons. And then last, competition STD NMR can be used to observe the effect of interfering species or additional species on nanoparticle small molecule interactions. So with that, I would like to thank the members of my group, collaborators, and also the NSF for funding, and thank you for your attention.
Thank you very much for the very nice talk. I don't see any question in the chat, so maybe I can ask mine. So I just had a question during the talk. Is NMR already used to, I don't know, analyze the water in cities to see if there are some nanoparticles already?
So you mean to try to detect, like, if we have water,
Yeah.
can we detect nanoparticles in the water?
Yes.
Yeah, so that's one thing we are working on in my group, and I'm sure in other groups as well. So yeah, that is something that definitely is in the works. Yeah.
Okay, and are there also other analytical techniques used other than NMR? You showed optical spectroscopy, but I mean already used in the industry or things like this?
Right. So ITC is a good one. So isothermal titration calorimetry is used a lot to determine binding. Yeah, I like NMR, so I use NMR a lot. In terms of proteins, there are a lot of biophysical techniques as well. They're often used, maybe less so with small molecules, but a lot of groups are working on proteins interacting with nanoparticle surfaces as well.
Mm-hmm. Okay, we have a question from Nesrine in the chat. So thanks for this very interesting talk. Regarding the water samples, could you explain on the methods you use to ensure the absence of pollutants, such as paramagnetic substances that might impact the relaxation or control the experiments?
Mm-hmm. Yeah, so we are not yet looking at like taking directly water samples like from the environment, not in my group in particular, but yes, that's definitely a concern if you have paramagnetic things in your sample, like with the copper EDTA, is going to decrease the relaxation times. Again, using the initial slope of the STD buildup curve should take care of that. You do have to be able to see it though. So if things are broadened completely, or if the T2 is too short, that may be an issue as well.
Mm. And so with STD, you cannot access the strong affinities, right? So is it possible to like hyperpolarize the ligand and then do a single scan T2 CPMG or a T1 measurement?
Mm-hmm. Yeah, so I know that Christian Hilty's group has been working on hyperpolarizing things, and yeah, so that's definitely something that can be done. And he compared his work to the STD NMR, but obviously the hyperpolarized work is going to give you much higher sensitivity.
Mm. Okay, we have two other questions from Shakt. Hey, Shakt. So thank you for the talk. When you see a significant STD effect, can you assign the effect to a higher KD or larger amount of binding sites on the NP?
So yes and no. So could be either or. For example, for the antibiotics, we actually didn't calculate a KD, again, because we couldn't access that range. So we can kind of say that if you see a higher STD effect, it could perhaps mean more binding sites, so more tendency to bind. And so that could be the case with the levofloxacin, for example. It could be occupying all the different binding sites and not allowing the other antibiotics to bind. Yeah, it you can kind of say that it could mean either a higher N, either a higher number of binding sites, or a higher KT. So both of those effects will lead to a higher STD effect.
We have another question from Draney. Can small acid molecules be used in this method when interacting with nanoparticles, such as lactic acid, for instance?
Yes, I don't see why not. Yeah, so essentially the receptor needs to be large enough so that when you saturate it, you saturate the entire receptor. So that's facilitated by slow rotational correlation time of the receptor. And again, that dipolar coupled network of protons. So yes, it should in theory be able to be used for any large receptor particle and any small molecule that's going to bind and associate with that receptor.
We have another question from Chileum. How do solvent properties influence the STD NMR analysis of small molecules nanoparticle interactions? And are there specific solvents or solvent conditions that are particularly advantageous?
So we've been using mostly D2O. So I feel like any solvent that is not going to significantly influence the viscosity should work just fine. Yeah, temperature will influence binding just in any case, but it should work fine with any solvent conditions. Basically anything that you're using for solution state NMR should work for the STD experiment. No particular considerations, really.
I have a remaining question. Is there some work to go towards imaging with like seeing if there are some nanoparticle in an organism?
Yeah, so there's definitely work being done. So there are papers out there looking at, especially for paramagnetic nanoparticles, to image and kind of look at the T2 or T1 as a function of position,
Yeah.
to sort of seek out where nanoparticles are. Yeah, there's definitely MRI and imaging has been used to detect nanoparticles as well, especially for the paramagnetic nanoparticles.
Okay. I have one other question. Does the STD exist also in solid state? The STD experiment?
So you'd need, I think it could be done. You would need the ligand to dissociate from the receptor surface, but in solids you're going to see it anyway. That is a good question. I think if you have something binding in solid state NMR, you're usually wanting to study the strong binding. So something that's going to be bound strongly, and then you can look at distances. You can get the distances directly from measurement of dipolar coupling and just NMR distance experiments. So I think in the solid state, it's sort of more useful for things that are strongly bound. Whereas the STD experiment is more useful in solution for things that are binding and then having that K off so that we can observe the transferred saturation that's been transferred in solution.
If I may have another question, but it's a bit out of the topic. For the polystyrene beads, you said they seem to be porous, but I think in your article you said you didn't mention any pores with these particles, right? So was that a surprise because it's commercial, is not specifying it's porous, but you observed it was porous. And is it possible to know with N2 absorption, for example, the pore size of these particles?
Yeah, that's a really good idea. I think it was not so much of a surprise as just kind of reminding us that these are they're polystyrene nanoparticles, and then they have a charged group on the surface. But we can't really think of them as a hard sphere with negative charges. We do need to think of them as being sort of porous or having some sort of wrinkles on them. It's not going to be a perfect sphere because this is a sort of a soft matter polymer. So just kind of reminding us that there's not like a hard surface. It's not a perfect sphere, but that it does have pores or sort of indentations and things that a molecule could get sort of enveloped in, not necessarily specifically binding, but different ways that this soft matter could sorb or adsorb small molecules.
So just Amrit gave an answer for the STD in solid. So he said dipolar coupling measurements using Respidoor or trapdoor measure heteronuclear distances by saturating the X spin. And variable frequency, selective low power saturation on the X channel, and observing the protons has been used to indirectly observe X spin spectra. So this answers the question for the STD in solid state. As if we add one question. So which alternative nuclei could prove beneficial for investigating STD? And can low gamma nuclei be effectively utilized for this purpose? And third question, how does the interplay of chemical shift dispersion factor into the study?
Good questions. So the fluorine nucleus has definitely been used in STD NMR. So that's one. Low gamma, we have done experiments where we have observed, we've done the saturation to protons and then transferred that saturation using an inept experiment to carbon. So you can do that in a 2D experiment or in a 1D experiment. So that could be also used for different low gamma nuclei. And the third question, chemical shift dispersion, meaning, like, is it difficult to transfer if the chemical shift is very different? Is that I don't know. You maybe don't have the
range of chemical shift. How does the interplay of chemical how does the interplay of chemical shift dispersion factor into the study? As if I understand well, you say between fluorine and proton, right?
I see. Yes, so fluorine has been successfully used in STD NMR experiments, and it obviously has a much larger chemical shift range than proton. If I suppose if the chemical shifts are very different, this saturation is not going to happen. But that's something that I haven't looked into as much. Yeah.
Okay, as if says great. Okay. I don't see any more questions in the chat. So highlight some seconds for people if they are writing questions. But with that, there is another one. Sorry. How do you deal with issues of spectral overlap and complexity, especially when dealing with nanoparticles with heterogeneous surface properties?
Yeah. So we've actually used, we find that we can saturate very far from where ligands might resonate. So we don't generally have an issue with overlap. So we've seen with these polystyrene nanoparticles, we'll saturate at 12 ppm. So generally, if you have ligands that don't resonate near 12 ppm, you can hit the receptor and you're fine. We've also looked at -1 ppm. So that's sort of the typical place where if you're looking at protein, small molecule STD, a lot of times you're saturating at -1 ppm, assuming that there are no ligand resonances in that range. So it's usually not a problem. We can usually find a frequency that we can saturate the receptor without disturbing the ligands. If you do disturb the ligands, there are techniques such as STDD, saturation transfer double difference, where you can subtract out that influence. So there are ways to handle overlap in different spectra.
There is another question. Are there any alternative nanoparticle preparation methods that might result in higher concentrations or more uniform samples, which could be more amenable to NMR analysis?
Yeah, so I can also highlight Vincenzo Vendetti's work. He's looked at putting nanoparticles in a gel. So he has a very nice paper where he's developed different gels for different nanoparticle ligand systems. And that allows the nanoparticles to kind of remain dispersed throughout the NMR tube and not settle to the bottom over time. So it allows a much more stable sample preparation. Our nanoparticles that we purchase seem to be stable even over up to a month or so, because they have these negative charges. So I would not say that they're dissolved, but they remain dispersed. So they don't tend to settle to the bottom. And we see that at least the 1D spectrum looks pretty consistent over time with these particular nanoparticles. But yeah, definitely check out Vincenzo's gel work. It's a very nice paper. Yeah.